So this is applications of separable differential equations. Let's talk about Newton's law of cooling. So an object which sits in a room with the ambient temperature T0, right? If the temperature of the object at time t is given by U of t, the temperature at time t, then Newton's law of cooling tells us that the rate of change of the object's temperature is negatively proportional to its deviation from the ambient temperature. Or using mathematical notation, the rate of change of the temperatures is negatively proportional to the difference or the deviations of the temperatures and the ambient temperature, right? Makes sense. Where K is a constant, is a real constant of proportionality, and it depends on the object's material properties. Again, du dt is the rate of change of the temperature. U is the temperature as time t, and T0 here is the ambient temperature. Well, we can answer this, try to answer the next question. So what should happen to the object's temperature if it starts out warmer than the ambient temperature? So if it starts out, if the temperature of an object is higher, warmer, right, than the ambient temperature, then using Newton's law of cooling, we can say that the temperature of the object temperature will decrease and approaching to the ambient temperature. Right? Decrease is acting negatively. So at first it started higher, then over the time, so this is T0 here, and this is U0. If it's higher, then over the time it will decrease, and it will decrease to approaching to this ambient temperature. Okay. So if an object, so the second questions, an object has cooling constants K is 0.25 and begins at 50 degrees Celsius in a room of temperature of 23 Celsius degree. You want to find the temperature of the object, right, after a T is positive time, T in minutes. So using Newton's law of cooling, we know that du over dt equals to negative k, and k is 0 to 0.5, right? Multiply to U minus the ambient temperature, and this is the ambient temperature right here, 23. Okay. Well, then we have a differential equation. Using Newton's law, we come up with a differential equations that we use other properties that this problem's providing us. Again, I'll show that this is K, and this is T0. This is T0 right here. Okay. Once you set up a differential equation, the task now is finding U. So what is U? In order to solve for U, and you look at this differential equation here, it's just the equations in terms of U, right? Differential equation du dt in terms of U, and we can use separable equations. So this is a separable. It's a separable equation. We can separate U and T to both sides. So then du divided by u minus 23 equals to negative 0.25 times dt. Okay, well, you can integrate both sides to solve for this equation. So integrate this, you have natural log of u minus 23 equals to negative 0.25 times t plus c. Okay, and at this point, u equals to e to u minus 23. I can get rid of the absolute value, equals to e to the negative 0.25t plus c. And then u equals to e to the negative 0.25t, right? Plus c, I can move the c up here because e to the c again. So e to the c, it's just a constant. So I just, instead of having c here, I just combine e to the c, constant multiply to the constant here, and I add to 23. So this is my u equation, right? U function that measures the temperature of this object in terms of T. And the units for T is minutes and the unit for U is Celsius degree. All right, let's do the next example. A cup of coffee is placed in the room of temperature 17 Celsius degree, and its temperature is 95 degree. Okay. So I just want to write down all the information I know. So I know that T0 here is 17. I know that the coffee temperature starts out as 95 degree. That means U of 0 equals to 95. All right. Again, I'm using U as a temperature, the coffee temperature. Another information is after 10 minutes, the temperature of coffee has dropped to 90 degree. So that means U of 10 equals to 90. Okay. Your goal is to find the temperature after T minutes after being placed in the room. So again, we just need to find U of T equals to what? What function for U of T? And because we are like measuring an object's temperature, right? Given the ambient temperature, so we can use the Newton's law of cooling. So the Newton's law of cooling is telling us that we know that du over dt equals to k, negative k, u minus t0, right? And we know that t0 is 17. So du over dt equals to negative k, u minus 217. All right. Now the question is, we need to find k. What is k? Once we find k, then we already we can solve for this differential equation. Again, this is a separable differential equation. Then we can use that method to solve this equation. So again, du over u minus 17 equals to negative k dt. Then you have natural log of u minus 17 equals to negative kt plus c. Okay, so I get to this point. And at this point, I have two parameters. I need to find k, and I need to find c. I need two parameters. That means I need to have 2 points. Luckily, I do have 2 points to work with. The first point is when t equals to 0, u equals to 95. Using this point, I plug t equals to 0 in here, you get 0, 95, natural log of 95 minus 17 equals to c. Then I can find c, right? So c is just natural log of 78. Well, once I have c, then I need to find k, right? And I can use the second point to find k, hopefully. So if I plug the second point into my equation, I have using u of 10 equals to 90. Then natural log of 90 minus 17 equals to negative k times 10 plus c, which is natural log of 78. Okay, now I can solve for k. So I move this around, it's gonna be natural log of 78 minus natural log of 73 divided by 10, approximately 0.0066. Okay. Well, I found k, I found c. That means I found my functions, my coffee's temperature function. So the function is, I need to plug k and c in here, right? So once I found k and c, I plug it in. So natural log of, let's go here. U minus 17 equals to negative 0.0066 t plus natural log of 78 is my equation. And then again, I want to solve for u, right? Explicitly, I can do that. I would take u minus 17 equals to e to the negative 0.0066 t plus natural log of 78. Then u equals to e to the negative 0.0066 t plus natural log of 78 plus 17. And again, the units is Celsius degree. And this is my equation, my function for my cup of coffee's temperature, right? So if you look at the direction field of the equation dy over dt, like du over dt equals to negative 0.0066 u minus 17. You can see that if as I say, that the starting point, the initial point is when t equals to 0 and y equals u equals to 95. This is where I start, and this is my solution curve right here. Okay, so this is a solution curve for this problem. All right, the coffee temperature problem. And you can see that is an decreasing exponential functions decreasing down, and as we know that it's approaching to the line y equals to 17 as the temperature of the coffee will approaching to the ambient temperature, which is 17. All right, and then if I You see that as t increasing, this is how the sphere is tracing the solution curve as t increasing or as time goes on. All right, so this is how you want to use Newton's law of cooling in order to find the equation that can model the temperature of certain objects, right? If that object is sitting in a room with ambient temperature, okay? And again, the temperature of the objects is decreasing or increasing depending on the starting point of the temperature compared with the ambient temperature. And the temperature, the rate of change of the temperature is negatively proportional to the difference between its temperature and the ambient temperature. And the K here is a constant of proportionality of the objects, and it depends on the materials that the object is made of. And again, once you have a differential equation set up using all the properties that you are given or you found, then you can just solve for a differential equation, and in this case, it is one of the separable equations. You can separate the two variables on both sides and integrate both sides to find u.